All right, so it should now be recording. The audio is on. All right, so let's also go back to the bright space and take a look at what we have there. Okay, so you can see here, this is the last module. I will do a summary module of these. This is something related to the lab equipment. If we don't have access to that this semester, so I'll do a review, just like a lecture of this. And then this is the last module, basically, of the semester. So let's take a look at what's in here. So you can see here, there's 4 files. These are the slides, and this is more of a cryptography review. Should have taken that in your ITS 350, and so today I'll just kind of review some of those concepts. And then here we have the PDF, that you should read also, the Seed Labs PDF on VPNs. Okay, so definitely remember this. I'll come up with a series of problems, or one problem, something, and then, but make sure you read this for your own information. Okay, and then finally, these 2 zip files that you see here, this one and this one, are related to the lab itself. So they're basically it contains the files that you will need to implement this lab. Now this lab is in C++ because it's the most efficient way to implement the VPN, but all the code is provided. Okay, so all you have to do is basically run it, right? And but it will require some configuration. So I'll talk about that. I'll start talking about that after the after the lectures, basically. All right, and then here, let's just take a look quick, before we start with the slides, let's just take a quick look at this PDF document. Okay, so let me close actually. All right, so let's take a look at the PDF document as well. So this is our virtual private network lab, as you can see. So we'll go over this. We'll take a look at some of these concepts like TLS and SSL, right? And we'll take a look at that again. We'll talk about, what is a virtual private network. We'll talk about this tool, TuneTap, okay? We'll talk about routing. We'll need to do a little bit of this. And then, as I said, today in the slides, I'll go over a review of this. And then finally, at some point towards the end of the lab, I'll talk about TLS and SSL. So we'll take a look at that. Now, as usual, you should read the respective chapters on this. So in particular, TLS and SSL, which is chapter 18 of your book, 18 and 19. So take a look at that one. Hopefully PKI is a concept that you're familiar with already from your previous courses. So that's basic ideas. And then here is sort of the network setup that we're going to create. You will need 3 VMs for this lab. Mitch, my graduate student, has also prepared a very nice video for you guys, but I just haven't posted it. So I haven't had time to post it, but hopefully by tonight, later tonight, you can check the calendar and there will be a new video. He put this in his own channel on YouTube. So then I'll just put the link on there and then you guys can take a look at it. It's basically the video is titled "Making a Linux VM into a Router." So that should be pretty interesting. So definitely take a look at it. But as I said, I haven't posted it. All right, and then so that's one of the things. So you can check out that video. It's only like 12 minutes. So it's a short video. And then after that, as you can see, we need to set up. We'll need to use VMware to set up our network here. And so we'll talk about this, but we'll have this concept of a VPN client, VPN server, right? And we're trying to make a VPN connection. So what that means is really we want to have a secure, confidential communication between somebody that is, let's say, on the internet and they can gain access into an internal network. So this 10.0.2 network would represent an internal network. So we'll take, and then this would represent like a router or a firewall with VPN functionality. But you know, all these concepts, I will go into them in a lot of detail. I don't intend to give you a lot of problems on this one because there's a lot of setup really. So it'll be more about, you know, you can expect like very few problems, but they're a little bit involved. But it should be pretty interesting. All right, and so this will be, as I said, you know, what I recommend is just start reading through this, lab. And I'll cover all these details later on. It talks a little bit about setting up the TuneTap network, so I'll talk about that. How to run the VPN client, VPN server, and then, of course, the encryption. I'll start with the encryption today. I should say with a VPN, you know, if you remember from your 372 or other classes, basically creating a tunnel is what? It's creating like an SSH tunnel or a telnet tunnel or a netcat tunnel, you know, some kind of a redirection of packets, right? And so a VPN is really, you know, if you want to think of it as a tunnel plus the encryption, right? So those are the two main elements. So before you know, the tunnel is a lot of networking and routing and things like that. So I will talk about that second, and then today I'll just talk a little bit about the cryptography, but basically just as a type of a review. Now, authentication, we'll talk a little bit about this as well, how you could do this. You know, usually, you know, some of the technologies involved in that, like a radius server and, you know, Active Directory. And then, as I said, you know, you'll have a couple of problems to deal with. All right, you can see this. It's talking about the etc shadow, so the shadow and password files for doing authentication. But we'll talk about all those elements later. Okay, so definitely start reading through this PDF. It's got a lot of useful information about the C code, etc. Okay. All right, so anyway, so I wanted to start with that, given that that's ultimately what you will be doing, just a VPN part of this. And then this, by the way, is your last homework. So we can make it either do a week from today or 2 weeks, or really just do the week of presentation. Not later than that, though, because I want to have enough time to grade it. All right, so that is, I wanted to say that, right? You can also start, if you'd like, you know, on your CVM, you know, start thinking about downloading these zip files, because you know, they got all the code in there. All right, so now let's get into, you know, so let's get into VPNs just a little bit, and then after that, we're going to start with the slides. Let me switch over. Let's switch over to the whiteboard just briefly to kind of lay out what we're talking about. All right, so first of all, let's start with the big picture, right? So let's start with the big idea. And so I think I've used this example all semester, so I'll just continue to use it. You have domains of trust, right? So you have domains of trust. So you have domains of trust, kind of like, oh, maybe I should use a different color for this one. So domains of trust like that. Okay, so where you have less trusted, to more trusted. Okay, and this is somewhere in between. Usually, you know, I'm using the traditional physical layout of a DMZ, the demilitarized zone. So then if we go back to this example, if you remember, we've said this is like switch 1, switch 2, switch 3. And then this represents, like the web. So the internet, insecure internet. This is just some kind of a router, maybe like an ISP. And then this is your firewall. Okay, that's your firewall. So then this would represent then your internal network, right? So this is the internal network of a company. So the internal network. Okay, you have some computer there, PCs, etc. The finance department, let's just say like an accounting computer. See? Okay, and so now you have in here several things, right? So if we remember, we're talking about, obviously this is the network, this is the internet, everything. Somewhere in the internet, you have a remote worker. So you have a remote worker. Okay, that's a person, and they have maybe a laptop, right? And the laptop then is a computer, where they do all their work. But there's a server on here, let's call it the data server, and they want to use that server for whatever work they have. Okay. Now the problem is, if you remember, the firewall does not allow anything that originates from the outside in, right? It doesn't do that. So you need to find a way to get through, right? So now, so far, what you probably know is that there is something called port forwarding. We talked about that as one of your problems, right? And you understand that, somebody could get to this IP and this port number, and the pre-routing and all those chains just, forward here and then maybe to that machine, right? So that is port forwarding. However, that is not very secure, as you don't want people to just come in from anywhere. Remember that anyone from the internet can get as far as there, right? They can get, as far as that. And so that's, not recommended, obviously. And so you want to think about, okay, port forwarding may not be the best solution. I need to have a solution that provides, some kind of an authentication. So it provides authentication of some kind, and, well, basically that provides the principles of information assurance, right? So let's go back to those. So what are the principles of information assurance? The important ones are confidentiality, right? We'll see this in the slides. Integrity. What was the other one? Availability, right? And so on. So we want to preserve these, authentication is one, right? Authentication. And so we want, port forwarding does not do authentication, not really. You could have a rule that says, well, if it came from this IP, but that doesn't help, because you guys know that with spoofing, you can always spoof that packet. So that doesn't work. All right. So then what do? Well, you need a service that provides authentication. What else? You need a service that provides confidentiality. Right? And you need a service that provides integrity. So what are these? They should sound familiar, right? They're the basic core principles of cryptography. So crypto then seems to be a solution plus authentication via an account. However, because you're coming from the less trusted or insecure environment, you can't really send passwords, etc., through the network like that in the clear text, so they have to be encrypted. So that basically means that you have to agree to have a technology. So the first thing you need to do is you want to establish, very much like we did with port forwarding, a kind of a tunnel. right? So you want to create some type of a tunnel, right? So you want this concept of a tunnel, and the tunnel is created between the remote worker and the firewall. Okay, and that's just really, this tunnel is nothing more than, like routing. So it's routing rules, right, etc. So those kinds of things, right? So we'll see that that's the part that I had said, that's the tunneling part. Okay. However, the tunnel here, if we use something like netcat, port forwarding, etc., all that, so that we can reach the inside network, well, the problem is, how do we meet these, right? And so that's the other component. We need to add the cryptography aspect. Oops, keep erasing that. Okay, and so let me erase here. All right, so then besides the tunnel, we need the cryptography. So we need crypto. We will need a couple of programs, obviously. So we would need code here and here, right? And then we're going to call this particular code here, we're going to call it the VPN server, right? Because a VPN is a virtual private network, right? So virtual private, so a virtual network, first of all, that's the tunneling. And then the private part is the cryptography element. On this other end, we need some additional code, which is going to be the VPN client. So it's just code, right? So it's just really code. This is provided in your lab, and this is going to be the C++ code files that you have that you will have to compile. Okay? Now, why is this code important? Because this code is basically like sniffing and spoofing, just like before, right? So you're going to create some packets, and the packets will know where to go, back and forth, right? And then after that, besides the code, we will need to configure some things on this device and on this device related to routing rules and tunneling, right? And that's a lot of, what a VPN would do. Once we've established all of that and we establish some communication in the clear text, then these two, the VPN server and the VPN client, have to agree on how to do crypto. They have to agree basically on how they do the cryptography. How do they, and the question then becomes, how do they achieve, how will they achieve these elements? How do you usually achieve integrity with encryption, for instance? How do you do that? So what's the keyword there for integrity in cryptography? Right, so we usually use hash algorithms, right? So hash algorithms, and then we have authentication. What about authentication? Okay, so PKI, right? So public key infrastructure, helps us to do authentication, exchange keys, and then confidentiality is usually done through some type of a symmetric thing, right? So we'll talk a little bit about this. As it turns out, all of that makes up a protocol that should be very familiar to you called SSL, right? The SSL protocol, secure socket layer, which is a combination of all of those. And then in this set of lectures, we're going to learn about TLS, which is the transport layer protocol, basically, that uses SSL, but as a protocol that can be implemented. So this is, the easiest way to think about this is that it's just going to be a series of libraries that we're going to use in our C code over here and in our C code over here. Right, so that's basically it. I'm not going to make it too complex or anything like that, but we really want to understand the basic underlying principles. Whenever you're developing, remember, something in the network that needs to be really fast, you should use a language like C, C++, right, which is the most efficient. Remember that unlike other labs where we could use Python, etc., it doesn't make a lot of sense to use Python with VPN, because remember that VPN is actually doing a lot. So it's very performance intensive. So if you think about it, right, we have something like this, right, and we're sending a packet from one end to the other. Remember, that packet has to be, we have to do everything with the routing, etc., but that's encrypted. So the packet has to be encrypted, right? And it has to be decrypted over here. And if you remember, encryption takes a lot of work, right? So for instance, you guys know that there's symmetric and asymmetric encryption, and both of them can do confidentiality. Which one of those is fastest? Symmetric or asymmetric? Which one of those is faster? So symmetric is faster, right? So block ciphers, you should remember, right, are faster than asymmetric. So we'll talk a little bit about this. As I said, that's why, kind of motivate this. We'll do a review of what you learned in your 350 class related to cryptography. And then after that, we'll know, you'll know basically when I say, in TLS, just use this or that. All right, and that's it. So a VPN, so in summary, a VPN, now in summary, a VPN, which is a virtual private network, is a combination of two things, right? It's a combination of two things, which are the tunneling, right? And then there's the crypto, okay? So it's almost like this is the network and that's the security, right? So the network security combined. Right, and then here, so just remember that when I started this discussion with more trusted DMC, less trusted. So the idea is that as you are moving in that direction, you're moving to a more trusted environment, basically. And so, like here in the firewall, everything is going to be blocked. Okay. So anyway, so let's start. Let's start then here. So I have a set of slides for this. All right, and give me a second here, guys. I'm gonna adjust my lighting here. Hold on. All right, sorry about that. I couldn't see because of the lighting. All right, so anyway, so now, so I've given kind of a little bit of motivation of what the VPN is, right? And I've also said that we have a lab that, you should start reading the chapter and corresponding chapters in the book, start reading the PDF, right? And now, as I said, what I'm going to do is just a quick review of cryptography a little bit, right? So let me switch over to the slides. So the slides are posted on Blackboard, so you can just, or Brightspace, sorry, you can just get them from there. All right, let me find these. Here they are. Let me share the screen. All right, so you should be seeing now the slides. All right, here we go. Okay, so today, as I said, this is just, a quick review of some of the concepts, of your 350 course in cryptography, right? And so just so that we're kind of speaking, we're all reminded of the same language. So we've got basically, as I said, when you talk about cryptography, you want to talk about some of the main properties, sometimes called the main principles. So we have confidentiality, authentication, integrity, right? And then we have a few others like non-repudiation, availability. But in particular, for our discussion, we're mainly concerned with these three, right? So what is confidentiality, for instance? Who can tell me? What's confidentiality? What does it address? So confidentiality would address that nobody can read your message, right? Your message stays a secret. Authentication is what? Authentication addresses that the person who logs in is who they say they are, right? So if you're a remote worker and you're connecting from maybe across the world into the company through the VPN, you want to authenticate via username and password. But when you send that username and password across the internet, it should be confidential. So encryption. And then integrity basically means, that the message cannot be modified in transit. Okay? And as you probably know, we use cryptography for all of these, right? All of these problems. Okay. There we go. All right, so the basic idea of cryptography is what? There's an algorithm, right? There's an algorithm that starts with, some message called a plain text. You're going to have some encryption algorithm. It usually takes some kind of a key, and then you perform some kind of an operation, maybe like an XOR operation, etc. That produces what is called the ciphertext, where the ciphertext is the, is basically a function encryption that takes, the plain text and a key. Okay, and that's basically what happens there. Now, if an intruder or a hacker, etc., tries to view that ciphertext, they can't really decrypt it if you have a good algorithm. So in theory, it should be a very random, very much close to randomness, what you have in that message. Once you have the ciphertext and the ciphertext goes into the decryption algorithm, so now you have a decryption algorithm that takes the cipher. Once again, it takes the key. It usually just kind of reverses the process and you get back the plain text. Okay? Now we play with this in several ways to achieve the objectives of confidentiality, integrity, and authentication. So we'll talk about those in these slides today. Okay? So encryption is the process of encoding a message so that its meaning is not obvious, right? And one would say as close to randomness as possible. Decryption, of course, is the reverse process, which basically means transforming an encrypted message back to its normal original form. And then the terminology you can see here, you have plain text and ciphertext. So plain text message, plain text is the message to be encrypted. Ciphertext is the encrypted message itself. So all that should be clear to you guys. And then stop me if you have any questions at any time. Okay. So what is the basic problem. What is the basic problem here? We have two parties, you know, Bob and Alice, let's say, and then we have Zelda or, you know, whoever, hacker in there in the middle, and they want to intercept the information, right? So given both parties, they need to communicate. But they need to, for if you look at the previous algorithm, we're saying that to be able to communicate, you need to have a key. And the key needs to be exchanged in some way beforehand, right? So once both parties know they have a key or the secret, then you can achieve confidentiality by encrypting and decrypting a message and sending it across the network. But the key question is, because, you know, let's say that Bob, you know, this is Bob, and Bob is in, you know, Hawaii, right? So Hawaii. And then we have Alice, and Alice is in Chicago, let's say, right? So how do they exchange the key? Because once they have the common key and they keep it a secret, they can, of course, write messages and send them to each other, maybe via email or whatever. As long as they don't share the key, it's going to be pretty secure. But the question is, how do they achieve the exchange of the key or the secret efficiently? So how do they solve this problem? What do you guys think? Right, so let's see. In person. Okay. So what do you mean by in person? They get on a plane, they meet at a coffee shop somewhere, and they exchange the keys that way? Is that what you mean? Yeah. So what's the problem with that, though? What if they need to communicate right away? Okay. Right. So as I was saying, the question is, they want to achieve confidentiality. They want to send. We already saw in the previous example. We already know what encryption is in its most basic form, right? To get a ciphertext that you can send across the internet, you need a key. And then to encrypt it and then to decrypt it, you need the same key and the ciphertext. The ciphertext can be easily sent via email or something, but the key cannot be exchanged via email, right? So then how do Bob and Alice exchange the key? Is it possible, or do they have to, as somebody said, fly over somewhere? Any thoughts? Okay, so as it turns out, there is a solution called asymmetric encryption. Okay, so asymmetric encryption is what solves this. Oops, and there are various algorithms for that. So we'll take a look at that. Asymmetric solves that asymmetric encryption. So once the key has been exchanged, however, with asymmetric encryption, you can just perform the rest of the encryption with simple symmetric encryption. Okay, and in that symmetric encryption, basically, if you remember from your classes, symmetric basically means block ciphers usually. And what are some examples of block ciphers? You remember the names of the algorithms? So there's DES, AES, right? So hopefully those ring a bell. So those are some of the block cipher algorithms, DES, AES, and so on. Okay. A simple example. Most of these, though, revolve around the idea of the original algorithm of the one-time pad or XOR. So, here, obviously, we're talking about modern types of encryption. After say World War II, not really encryption based on. We're not really talking about encryption like in the Roman times, or because those were just like substitution or those kinds of algorithms. I can't remember right now, but substitution or shifting or whatever it is. Here we're talking about more modern types of encryption, since basically Claude Shannon and his one-time pad, so which are mostly based on the XOR operation. So I'm sure this is familiar to you, where you take XOR, right? So we all learn, everybody that learns a little bit about computers, knows what XOR is, the truth table, right? So you guys remember that. So in this case, for instance, the XOR operation, what is this? 1, 2, 3, 4, 0, 1, right? It's just an operation, kind of like that. And then you take the next. So this is the plain text. This is the key. Right? And we perform it based on the truth tables. We arrive at a solution. So whenever they're unequal, it's a 1. Whenever they're equal, whether it's a 0 or a 1, it's going to be 0. So we have that, and then 1, 1, 1, 1. You see that? And that gives us exactly this one over here. So that's just a truth table. So as it turns out, XOR, if you remember, is a very widely used computation for symmetric encryption. So when these algorithms of DES and AES. Okay. Now the problem is with the one-time pad, which was Claude Shannon's original idea, is that the cipher achieves perfect secrecy only if there are as many possible keys, or if the key is the size of the plain text, basically. So that's really what this should say. So the key should be the same size as the message. You can't reuse it. But the problem is, what if your message is a movie? That you can't have a key that big. It's just not practical. And so that's why messages have to be broken into blocks of, let's say, 256 bytes or something. And then you end up with keys of size 256. And so each block, you XOR the blocks, and you arrive from your plain text and your key to your block cipher. Right? So this all should be familiar to you. So now the advantage of using things based on the one-time pad or XOR is that it's easy to compute. Performing an XOR, a bitwise XOR operation on a computer is very cheap. In fact, in the hardware, computers are really made to do that anyway, so it's really fast. And that is, again, really important because, if your VPN is too slow, no one's going to use it, because no one will, people need to use their network fairly fast. Okay. All right. Encryption and decryption are the same operation, and they can be pretty secure. So it has been proven that they're widely used, right? So AES, etc. Those algorithms based on XOR are still used today, and they're widely used. Now the problem again is, it's not the issue of the XORing operation, right? But the issue of how do we exchange the key. So how does the sender communicate the key to the receiver? And then, as I was saying, secure key exchange is the fundamental problem. Okay, and that's why we have PKI. So you probably remember what PKI means. So public key infrastructure. right? So asymmetric encryption is the public private key infrastructure, or PKI, which is based on an algorithm called RSA, or algorithms similar to RSA. Now, keep in mind that our goal was at the beginning to achieve confidentiality, integrity, and authentication, right? So that was the objective. And so far, we have learned that by performing an operation XOR, we can go from a plain text using a key to a cipher. So that achieves possibly, some of these principles, right? But we still need to exchange the key in some way, and that's where, whereas to encrypt a message, we use symmetric encryption. Usually to send the key, we use asymmetric encryption. Now, we could use asymmetric encryption also to encrypt the message and achieve confidentiality. The problem with that is that block ciphers are much, much faster than asymmetric. So PKI is slower, right? PKI is slower. And then AES, for instance, which is a block cipher, is faster. And that's really important. So really what we end up doing is that for confidentiality, we use block ciphers. And for the key exchange, we use asymmetric encryption based on PKI. Any questions about that, guys, so far? All right, no questions, it seems. All right, so as we talk about cryptography, obviously we're talking about VPNs now. And so, we want to relate this to the fact that we're going to be performing cryptography in the network. So we're performing cryptography at the the network, basically, right? And we have to think at what layer of the OSI model it'll be that we perform this. So that's why if you're, you guys have, you studied the OSI model. So you have your Ethernet, your IP, your let's say TCP, and then some application layers up here. And then somewhere in between, there's actually a protocol, like a little thing that can slide in here, right? And that is going to be based on all of these principles, right? So as you know, when we talk about block ciphers, asymmetric, symmetric, we're talking about the primitives of cryptography, which make up basically a protocol SSL, secure socket layer, and then secure socket layer has been made into TLS, right? And so basically TLS is the block. Let's say it just squeezes in here. TLS is the block in the OSI model that does this for us, okay? That will do the cryptography as part of the model. So as we will see later on, this is how it fits into the entire OSI layers. Okay, so these protocols will provide all the functionality that we need for confidentiality, etc. So you can see here, they can authenticate messages, provide encryption, authentication, and integrity, okay, which is what we want. And so this, as you can see, is a tool widely deployed for VPNs or virtual private networks. And so that's how that fits into it. The other aspect is, as I was saying, that VPN will handle all the networking, the tunneling, and that's achieved through routing rules, etc. And all the authentication, etc., will be achieved either through cryptography, which you should know what these are, or also through just regular, as an additional element, authentication of username and password as well. So that can be achieved. Right, here's a scenario of what is what's going to happen here as we think about security of your IPs. So pretty much the example I had given before, you have host A and host B. You can think of these as routers, right? That's, of course, the insecure internet. And so what you want to do is before you send out a packet over the internet, you have to establish a secure tunnel between, you know, between your devices, right? You create that tunnel, you know, and that's just basically the software on both ends of the gateways that just make an agreement on a set of keys for authentication, a set of keys that they will use for confidentiality, you know, and so on, right? And so on. And then after that, the packets basically, if you notice, when you know, this would be, let's say, the normal packet. This is the normal packet. Before it's sent out into the network, it has to be processed by the code, and then it's encrypted, and it becomes the payload of the new packet headers, right? You can see now you have, you know, a new header there that allows you for that protocol, let's say like TLS, and then the packet itself, right? You know, I know it's already written there, but you can see it here, I guess. You know, this one, right, becomes just a payload of the other one. And we've already done this, right? We actually already did this. We talked about it in the firewalls lab when we were talking about firewall egress evasion. You saw that, what did we see? We created an SSH tunnel, and then we were able to send the packets through that. So that's effectively the same principle that we have here. Okay. So as we will see, you know, in the OSI model, as I said, you know, you have several layers that can be used for encryptions, like the application SSH, etc. You're familiar with that one. But in our particular case, we will be using SSL and TLS, which you can think of them, as I said, as a library in C, C++, or in the OSI model as one of those blocks that provides encryption, integrity, authentication between two communicating applications. Okay. This is SSL, in essence, comes down to RSA for key exchange, and then confidentiality with symmetric keys, right? So all of these are concepts from 350. And that's it. That's ultimately what we're still doing, okay? What we're still doing there. All right, so please, you know, if you have any questions, stop me at any time. Cryptography obviously can be used for other things like the file system, but, you know, that's not relevant to VPNs right now. All right, or is there anything? No. All right, so now what I'm gonna do now is just go over a little bit of symmetric and asymmetric encryption, as you can see here, and then we'll do some fun exercises just to make sure that you guys have this, haven't forgotten this. Remember, all this will be on the exam, final exam. All right, so I love this topic. I gotta be honest with you. I really just find it so interesting. So anyway, cryptography, right? So we have symmetric and asymmetric encryption. And SSL, as it turns out, will use both. Okay, SSL will use both. So we've already established that to exchange the keys, we use asymmetric. Once we have established the keys, then we can use symmetric. So whenever we think about cryptography, we think of two parties. So usually the common thing is to talk about Bob and Alice, right? So Bob and Alice are always in cryptography. And so here we have Bob and Alice, and they want to communicate. And then we have Zelda, you know, who's snooping, sniffing the traffic, right? And she wants to intercept it. So obviously, you need to make sure that everything is secure. If you're using the VPN, as we saw before, you want to make sure that everything is pretty secure. So the two most important techniques in symmetric encryption are DES, which is, it's not secure anymore, and then AES, which is a more, the advanced encryption standard is more secure. But they are basically just block ciphers, right? So as I said before, a block cipher is the main idea. The algorithm is a little bit more complicated than this. They have different modes of operation. Also, I'm not going to get into all that. But basically, just think that we have a message. We break it up into blocks. Then we have a key, let's say, of the same size. And this is block 1, block 2, block 3, block 4. And then all that's going to happen is when you want to encrypt your message is you XOR it, right? So you XOR all the value, all of those. And then you send the message over the internet. And AES and DES, they're pretty much based on this principle, but the algorithms just have a little bit more complication. The key sizes are bigger, etc. Okay, so this assumes, though, that the key has already been exchanged. So as I said, block ciphers just process the input one block of elements at a time, produces an output block for each input block, and this is the fastest. It's much faster, so that's why you usually want to do this. So I always give the example, right? So if you want to watch your Netflix movie, right as soon as you buy it, you're going to need to encrypt it with block ciphers, because if you use asymmetric encryption, you'll start watching that movie an hour from now or something like that. Okay. Properties of symmetric encryption. So in symmetric encryption, pros, confidentiality. CELDA, CELDA is, remember, the person that's trying to sniff the packets, so cannot access the message without knowing the key. Authentication, only whoever knows the key can participate in the communication, so that's a type of authentication. And integrity, if the message C is modified, it will decrypt to gibberish. That's usually true, right? So it's not going to, if it's been modified in some way, it's not going to work out. The cons of block ciphers, however, or symmetric key encryption is that key distribution is critical and requires out-of-band communication. And we can't just fly around the world to a coffee shop to exchange the key. Imagine, every time that you go to Amazon or your bank, you're basically doing encryption. So you wouldn't, you can't really just, every time you want to go to a new website like that, you can't travel to exchange keys. Now, another problem with this is symmetric key is that if CELDA, the sniffer, was able to compromise the key, then of course they could impersonate Bob and Alice, right? So they could just be in the middle, and so that's a problem too. And this cannot be proved, cannot be used to prove that a message was sent by specifically one of the involved parties. Right? So that's also not possible. Okay, practical issues. Symmetric key encryption is applied to a unit of data larger than a single 64-bit or 128-bit block. So I kind of alluded to that here, right? So you break it into blocks. The sizes, I mean, that just depends on the algorithm, your choices of parameters. But it's usually like 128, 256. And then there's a few modes of operation. I talked about that. And the modes of operations just talk about how the blocks are distributed. Are they treated independently? Are they treated sequentially in some way? Because some modes of operation might be more insecure than others. You probably remember this exercise from 350, where we could actually see that the electronic code book ECB mode was actually pretty insecure. So the limitations of symmetric key encryption are that, or sometimes called secret key, is the fundamental limitation of symmetric secret key encryption is how do two parties agree on a key. So in order for Alice and Bob to communicate securely, they need to agree on a secret key. In order to agree on a secret key, they need to be able to communicate securely. So it's like a chicken and egg type of problem. So this problem is especially common in the digital age. We constantly end up at websites with whom we decide we want to communicate securely, like Amazon, your bank, eBay, etc., Netflix, but with whom there is not really an option to communicate offline, to agree on some kind of a secret, right? So in fact, it's usually all done automatically, browser to server, right? And that's where PKI comes in. And for the browser and server, there's not even a concept of offline. They only exist online. So we need to be able to establish secure communications over an insecure channel. And symmetric key encryption cannot do this. So if you remember, when you're talking about a browser here, let's say this is your browser. That's your browser, and then this is a server over the internet. So let's say this is Amazon server, and then this is your browser. So what you do is, first of all, you want to communicate securely. But to be able to send encrypted packets, you would need to have a key and an agreed key, let's say, an agreed key. So before you can establish that you have the agreed key, you have to figure out how to send the key, right? And that's where, if this is symmetric encryption, and then before this, you need another connection. Right? And that's going to be called asymmetric encryption. Okay? So the asymmetric encryption is some kind of a way that you send the key. You exchange the key. Once the key has been exchanged, then you can do the rest of the work. So that's where asymmetric encryption comes in. Asymmetric or public key encryption. In symmetric encryption, public key cryptography, both communicating parties, Bob and Alice, have two keys of their own. So now, think about this. If we go back to the previous example, to exchange this key, which is the same one, we're saying that we need to use asymmetric encryption. To use asymmetric encryption, the browser needs to have two keys. Let's call it key pub and key private. And oops, that doesn't. Key private. All right, and on the other end, the server also, the server needs to have key public and key private. So as I said, this is just a review, so you should remember that asymmetric encryption works this way, right? So now if you think about it, there are 5 keys. 1, 2, 3, 4, 5. There are 5 keys involved. 2 belong to the browser, key pub, key private. 2 belong to the server, key pub, key private. They're unique to them. And then they're going to use those to create this tunnel, a secure tunnel between. Once they have that, they're just going to send the key, this one, and that's it. Once they have that, and then all communication and related to confidentiality will be done through that key over here. Does that make sense, guys? Are there any questions so far? No questions, it seems. All right. Okay, so I was saying, as part of the VPN, we need to do the same thing, right? We need to send all our data, so we need a way to send the key for the block ciphers. And asymmetric encryption now provides this. an asymmetric public key, or PKI, sometimes called PKI, cryptography. Both communicating parties, both Alice and Bob, have two keys of their own. Okay, just to be clear, that's 4 keys total plus the symmetric key, that's 5, as I had said before. Each party has their own public key, which they share with the world. So that means the public key of each person is available to everyone. Everyone can see it. And their own private key, which they keep secret or private. Right? So that's how it works. So the magic, though, the magic, and by magic, actually that should be the math that provides the magic. So the magic of the public key cryptography system is that a message encrypted with a public key can only be decrypted with the corresponding private key. Okay? So for instance, we'll do some exercises with this, but so for instance, Alice will encrypt her message, which usually her message will just be the key, right? So she's trying to send the symmetric block cipher key so that then after Bob receives it, they can communicate with it. So Alice will encrypt her message with Bob's public key. And even though Zelda knows she used Bob's public key, and even though Zelda knows Bob's public key herself, she will be unable to decrypt the message. Only Bob, using his corresponding private or secret key, can decrypt the message. Of course, assuming he's kept it a secret. Okay? So that's basically the idea here. Okay? Any questions about that? All right, doesn't sound like there's any questions. Okay. Great. All right, so now, so now let's just take a look at the, as I said, the exercises. So we have here Alice and Bob. So think of them as VPN client and VPN server, right? So they're both somewhere. Then you have Zelda in the middle. This is the web, right? Zelda's trying to snoop or sniff the packets. So then you have Bob and Alice here, and Alice has her private key and her public key, just like Bob has his public key and his private key. So then the message is going in this direction, right? It's going in that direction. So that means Alice is trying to send a message. So she's going to grab the plain text, let's say the symmetric key, and she's going to encrypt it with some algorithm like AES. What does she need as input? She needs to grab Bob's public key, but Bob has made that key available, right? That key is actually, let's say, on Bob's website or something, so you can always just get Bob's public key. All right, and now you take that public key, the plain text message, you encrypt it with AES, your algorithm, you get the ciphertext, right? Then you send the ciphertext over the insecure internet. So it's sort of like it leaves the VPN client and it goes to the VPN server across the insecure internet. So then Zelda, maybe she grabs the ciphertext. She's got Bob's public key, so she tries to decrypt it. But the problem is that message will only decrypt with Bob's private key. And Bob's private key is, a closely guarded secret of Bob, so Bob is not going to make it available. Therefore, Zelda cannot snoop. Once the ciphertext arrives, once it arrives through the firewall or it arrives through Bob's VPN server, Bob then takes the ciphertext, is going to take the corresponding decryption algorithm. He's going to use his private key because he knows that this is going to him, and it was encrypted with his public key. And now he's able to decrypt it and obtains the plain text. In this particular case, probably the symmetric key that he can now then use for everything. Now, I said something incorrect here, actually. I just realized. I said that for encryption and decryption, we were using AES. So I was obviously not thinking about that. That's not true. You would use something like the RSA algorithm, okay? For private and public key cryptography, you do not use AES or DES. Those are just for symmetric encryption. Here, for asymmetric, you use RSA or something similar to that. Any other questions? All right, so it doesn't sound, so everything's going well, seems. All right, and then if we move on. So asymmetric public encryption, it's impossible to overstate the importance of this. Alice and Bob do not need to plan anything ahead of time to communicate securely. They generate their public-private key pairs independently and happily broadcast their public keys to the world at large. Alice can rest assured that only Bob can decrypt the message she sends because she has encrypted it with his public key. So all this security is based on the fact that for many years, RSA is an algorithm that has not been broken, right? So at least it's not publicly known if it has been broken. It's possible that there are some governments out there that have broken it. That's possible. But as far as publicly, it is not known that it has been broken, so therefore it is trusted. Okay, we're obviously, the specifics of how RSA works for asymmetric encryption are something covered in 350, so I'm not really going to cover it here. We don't need it for this class for the VPN. We just need to have a, refresh our memories on what is SSL so that we, when we implemented the TLS. Okay. So it's very, very important, though, for the key exchange. Now, the additional question, so that, by the way, achieves confidentiality. Because, yes, he's received a message only he could read. And the message claims to have been sent by Alice. But how does Bob have a guarantee that it did, in fact, come from Alice? So that gets into the idea of how do we authenticate, right? So usually whenever we think of authentication, we think of usernames and passwords. But as it turns out, we can also authenticate with cryptography, right? We can use, again, public key infrastructure, RSA. Based on this duality of public and private keys, we can use it for authentication as well. So now let's think about that. How do we authenticate? So think of the scenario. What if Alice could encrypt a message with her private key that is decryptable only with her public key? Okay? Since everyone knows her public key, you may well ask what would be the point of that, right? So everyone can decrypt it. Because this message would be readable by anyone. But the important point is that only Alice could have created it, because only her private key produces messages decryptable by her public key. So in a sense, this is a type of authentication, right? If I can take a message, encrypt it with my private key, send out that cipher, and then everyone can use my public key to decrypt it, well, only my public key would have decrypted it. So therefore, that is a way of authenticating that it came from me. That's like, if I sent out the final exam, right? And the final exam, I use my private key. I've given you guys my public key. So when you receive it, you actually can check, well, it came from me because you're able to decrypt it with my public key. Okay, so that's a way of doing authentication. So this provides a form of authentication. So if Alice's plain text message is M, and she first encrypts M with her private key, then with Bob's public key, Bob can take the message he receives and decrypt first with his private key, that's for confidentiality, and then with Alice's public key. And at that point, he recovers the message M, but also obtains authentication. So this guarantees, the guarantees are that only Bob can read the message and only Alice could have sent it. Okay? And this is better probably visualized in this graphic here. So let's take a look at it. So the message here is going from Alice to Bob, right? So it's going from Alice to Bob. So Alice, using PKI, asymmetric encryption, the RSA algorithm, will take a plain text message. She's going to take an algorithm, so she encrypts with Alice's private key. So she's going to use her private key, right? When she uses her private key, she's achieving what? Authentication, right? So she produces cipher 1. Then she takes that cipher 1 as input and encrypts it with Bob's public key. At this point, only Bob. Here, everyone can decrypt it, but here, only Bob can, right? So at that point, before it leaves the network, it's encrypted with Bob's public key. And so it produces from cipher 1, it goes to cipher 2. At that point, cipher 2 is sent out on the insecure network. So here's Zelda. She tries to sniff the traffic, but she cannot decrypt it because only Bob's private key can decrypt it. Then it arrives at Bob's VPN, it goes through and the firewall, etc. He receives cipher 2, and Bob then decrypts with Bob's private key. At that point, only he could have decrypted it, and now that achieved confidentiality. Now it becomes cipher 1, the original cipher 1, and now everyone can decrypt it, including Bob, using Alice's public key. But at this point, what this proves is that it came from Alice. So it's authenticated, and then Bob ends up with a plain text message and achieves both confidentiality and authentication. Okay? And so this is a pretty important concept. Any questions? All right, doesn't sound like there's any questions. All right, good, good. All right, so those, again, remember, all I'm talking about is the primitives, so, block ciphers and symmetric encryption, and this is asymmetric encryption. Remember, at this point, probably what you want to send here is the key. The symmetric key that you will use with AES and, in the block ciphers, that's what would be your plain text, right? And RSA is only used for the key exchange. Now, let's think a little bit, now that we know these concepts, a little bit more formally about public key certificates and everything like that. So the last element that we need to add is integrity, right? Integrity is what? Integrity is that no one has tampered with the data. The data has not been, tampered with in any way. And so usually this is achieved through something called a hash function, which you can see them here. Right, hash function. And a hash function is very, very simple. It's a function that takes a variable length input and converts it into a fixed length output. So you can have a document, a file, etc., a book, right? And you run it through a hash function, and it basically just gives you a hash number, maybe of size 128 bytes or 256, but it's always a fixed value, and it's a unique number for that file. No other file could generate in theory, that number. So it's unique, and therefore, if somebody changes even just one bit of that file, the entire message will not decrypt correctly. So now let's think about all of this combined. So let me make this a little bit bigger. That should be. All right, yeah. So here we have, what do we have? We have, on here we have the, oh, I can't write like this. All right. So here we have the, for Bob, right? So we have Bob, and we have Bob's information. We have Bob's public key. But now we need some way of authenticating Bob, so that Bob is who they say they are. And this is where you have to trust someone. And usually that is called a certificate authority. And the certificate authority will basically sign things. This is called, like signing. So the process is Bob has a public key. And then there's the certificate authority, and then there's Bob's information. All that information in that file is run through a hash function, which generates a hash value. So it takes a variable length input, produces a fixed length output. This hash number is then signed, or another way of saying it is that it's going to be encrypted with the certificate authority's private key. What does that achieve? It achieves that now that message is only decryptable with the public key of that certificate authority. And therefore, the certificate authority authenticates that file. Now, remember, certificate authorities have to be trusted. They're highly regulated, kind of government supervised entities, like companies like VeriSign and so on, right? And so basically, it takes the data, hashes it, takes the hash number, and that hash number is encrypted with a private key to the certificate authority. That hashed value is called a signed certificate. It is basically annexed as a little piece to the file, and that is made available somewhere. Then, on the receiving end, then you have basically, you take the message originally again, you hash it just like you did here, which generates a hash value, right? And then what do? You easily just take the certificate authority's public key, which is available for everyone, and this is usually just stored in browsers, and then the browser just takes the, it's public and private key, right? So it uses RSA algorithm. It'll take this hash value, and if it was encrypted here, then here it's going to be decrypted. Okay, so it's going to be decrypted using, remember here, we use the private key. You see that there barely, and then here's the public key. So if you look closer, you'll see public key, private key. Okay, and then what does that give you? It gives you the original hash, right? So this hash is over there. And then now, because you also calculate it here, you just compare the two to see if they are equal. If they are equal, great. Integrity is achieved, authentication is achieved, and so you know that the keys are also correct. You see that, guys? And that's the whole mechanism, so that we can have secure communication between two parties. Any questions about this? All right, sounds like it's pretty clear for everyone. Okay. All right, and then the last thing then, let me add just one more slide here. Let me stop sharing. So now that we've talked about all these primitives, we can talk about SSL. So we are ready, I think, to talk about SSL. And SSL, remember, is the stepping stone to TLS, which is what we will be using as a mechanism to secure our tunnel. Now we won't do all of this. Obviously, it's a lot of work, but at least now we have a good review background of the crypto aspects, and then it'll be more familiar when we take a look at this in the VPN. So now that we've covered all those primitives, we can basically talk about SSL, the secure socket layer, and how it works, right? So it's going to be from here that we establish communication. So we have two parties, Bob, I'm going to keep it general, Bob and Alice. Maybe you can think of it as this is a web server, a browser, and this is a server, right? So you can because usually that's helpful to think of, or a VPN client, VPN client and VPN server. You can always think of it that way, okay? And so now what needs to happen is with SSL is first, you need to have public and private keys. So you need to have Bob, so let's just say the public and the private, and then here, public and private. Right? Somebody initiates the communication. Usually the browser will connect to the server, right? So you're going to Amazon to buy something. So then you're going to go in there, and now you have to, the first thing you want to do is you want to exchange the keys, right? So you send some information to the server. You could send them, for instance, your public key. Right? You say something like, I want to communicate. I'm going to send my public key. Remember, you don't just send the public key, but you send the public key as if it's been signed certificate by a certificate authority, right? Because Amazon probably knows, let's say, VeriSign. Or the other way around, your browser knows VeriSign, right? So VeriSign sign, let's say the public, so this is Amazon. Right? So VeriSign has signed Amazon's public key. So then Amazon will send that to you. Right? Hey, here's my public key. Now send me encrypted information. So then now the browser uses that public key to encrypt, right? Only, so this is now a cipher using, the servers, Alice's, I guess, Alice public, right? Only Alice can decrypt this with her private key, and that's how the process begins, right? So then you can use these keys, the asymmetric public and private key infrastructure to exchange keys. So then let's just say PKI to exchange keys. You also can use integrity, so use hash, right, and certificate authority signature to achieve integrity of the key and authentication. And then once the key has been exchanged, you also achieve confidentiality, right? So the symmetric key, let's call it the AES key. So the AES key is received with confidentiality. Right? So you receive it with confidentiality finally, because now when you start using the public key, right? The public key, then at that point, you can send information with confidentiality. And then once the key is exchanged, then at that point with SSL, you start now the communication. So if you start buying products, or let's say it's Netflix, you're exchanging a movie or something, everything after that gets encrypted with the AES key, the block cipher key. And remember that that's because AES, or the symmetric key, is going to be much, much faster than PKI. And that's it. That's basically SSL in a nutshell. You know, in summary, you start with the asymmetric encryption for the key exchange. You use some aspects of certificate authority and hash for integrity and authentication. And then finally, once the key is exchanged, kind of out of room here, but you now exchange data securely. Okay, and that's basically SSL. So that's the same for everything else, for the VPN, you know, or whatever it is. Obviously, with VPNs, you have a little bit more of control, right? Because now let's talk a little bit about the scenario of VPN. We actually have VPN VPN clients, or sorry, let's say VPN. What is it called? Sorry, this is VPN. Let's group them VPNs into remote user. So let's call it remote to site VPN. And we also have site to site VPN. Regardless of what it is, which one it is, at the end of the day, it's just software that's running, right? So the only difference is that with remote to site, with remote to site VPN, what do you have? You usually have, let's go back to the original drawing. This is the web. This is the firewall with VPN capabilities, right? And so here is where you have like the public and private and all the algorithms related to cryptography, okay? And then on the other end, the remote worker has probably like a laptop, but the laptop also has what? A VPN client, a little program. Usually, what's it called? I think on my computer, it is what is the one I use? Can't remember, but Semantic or something like that. I can't remember right now. Something. Anyway, you have a VPN client, right? And that's just software. And so this software, basically, they will, you know, do all this communication, right? So the public and private key, as we described, then send the secret key, and then after that, exchange information. The difference is the software runs on a device here, on a VPN device, like a Cisco ASA, and over here on your laptop, you just have a little program that you install. Okay, your VPN client. That's remote to site VPN, the remote worker to site VPN. The other alternative is site to site, and it's pretty much again the same idea, site to site VPN, and that's where you have, in this scenario, you know, a little bit more complex. You have, let's say, the internet. Okay, so you have something like this, and then you have something like this on the other end. Right. So remember here, what you have is you have a firewall and a router, and this is a router and a firewall. So this is the internal network, right? So the internal network is about here, and this is the internal network. So let's call this, company. It's the same company, but let's say site A and site B. So they're both connected, you know, to the internet here. And then all that happens is, again, you have VPN functionality, maybe on from the device, the network device, but now it's 2 devices at each site. And again, they're just software running on these devices. And that's why it's called site-to-site VPN. So it's devices now. All the workers are here, and they just use those devices basically through routing and everything. And so again, the software needs to have public, private, public, private to achieve the basic objectives of exchanging the key. Once the key has been exchanged, they can just use their protocols, and that's it. That's the basic idea. Okay. So today, in summary, we've talked about, we did a review of your cryptography knowledge just to kind of refresh your memory. And then we talked a little bit about the big picture of VPNs. Now what we will do in the next class is that we are going to talk about the other portion, right? So we're going to talk about a little bit about how to set this up, a little bit of the routing, and get more deeply into the lab. So how we can do this exercise of creating the tunnel for routing the packets, and then talking a little bit of how we can achieve the cryptography part through, as I said, the protocol is called, usually is sometimes called SSL TLS, or TLS itself. Okay, and so that's basically it for today. I just wanted to do a lecture, kind of a review of the cryptography and the big picture, and then on Thursday we will get more deeply into the lab. Remember, this is your last topic of the semester. Okay, so at this point I'm going to pause the recording.